Imagine rain so acidic it could strip paint off your car. In the 1980s, that wasn't imagination, that was Tuesday in places like the Adirondack Mountains. Over 200 lakes became so acidic they turned crystal clear because nothing could survive in them. The pH dropped to around 3.7, about the same acidity as soda. Statues that had stood for centuries dissolved like sugar cubes. Scientists warned we were witnessing an environmental apocalypse in slow motion. Then governments listened, and the greatest environmental recovery you've never heard about unfolded. But here's the strange part, we completely forgot it happened. The forgotten environmental apocalypse. Here's the thing about environmental disasters, we remember the ones we didn't solve. Chernobyl still haunts us. The ozone hole occupied headlines for decades. But acid rain, the environmental crisis that had scientists predicting the death of entire forests and the sterilization of thousands of lakes, just disappeared from our collective memory. One day it was everywhere, the next day it was nowhere. Which is strange because for about 2 decades, acid rain was the environmental boogeyman that kept everyone awake at night. Picture this, it's 1985 and you're driving through the Adirondack Mountains in upstate New York. What you see looks like something out of a post-apocalyptic movie. Entire mountainsides stripped bare of leaves, their skeletal branches reaching toward gray skies like the arms of the dying. Trees that had stood for decades now reduced to bleached wooden tombstones. The forest floor, normally thick with undergrowth and buzzing with life, sits empty and silent. This wasn't the result of a fire or a plague of insects. This was the work of rain. The lakes told an even more disturbing story. In the 1980s, more than 200 lakes in the Adirondacks had become so acidic that they could no longer support fish. These weren't small ponds either. We're talking about bodies of water that had sustained ecosystems for thousands of years, now rendered lifeless by precipitation with a pH lower than orange juice. The water looked pristine, clearer than it had ever been because there was nothing left alive in it to cloud the view. Local fishing guides watched their livelihoods evaporate as anglers stopped coming to fish in dead lakes. The destruction wasn't limited to remote wilderness areas. Ancient limestone buildings and monuments that had survived wars, natural disasters, and centuries of weathering began dissolving at an alarming rate. The Statue of Liberty's copper skin turned green faster than expected. Gothic cathedrals across Europe watched their intricate stone carvings melt away like ice sculptures in summer heat. In Athens, the Parthenon suffered more damage from acid rain in the 20th century than it had in the previous 2,000 years combined. But the real horror show was happening in Germany's Black Forest, where entire stands of spruce trees were dying from the top down. German scientists coined a term for it, Waldsterben or forest death. By the mid-1980s, more than half of Germany's forests showed signs of damage, with sites like the Black Triangle seeing over 50% of trees affected according to Swedish Environmental Agency reports. The phenomenon spread across Central Europe like a slow-motion plague, with similar devastation occurring across multiple continents as forests collapsed under their own weakened weight. The international blame game that followed was unlike anything the environmental movement had seen before. But here's where things get interesting. Back in 1977, the OECD had published what they called a blame matrix, research showing that sulfur compounds could travel hundreds of miles through the atmosphere before falling as acid rain. This was a pivotal moment when policymakers first realized that pollution didn't respect borders. Countries pointed fingers across borders with the fury usually reserved for trade disputes or territorial conflicts. Canada accused the United States of poisoning its lakes with sulfur dioxide from Midwest power plants. The Scandinavian countries filed formal complaints against Britain, claiming that British coal plants were killing Norwegian forests and Swedish fish populations. The situation became so tense that acid rain featured in high-level diplomatic meetings between world leaders. For anyone who lived through the 1980s, acid rain was unavoidable. It dominated news cycles with the same persistence that climate change does today. Time magazine ran cover stories with headlines like "The Poisoning of America." Television specials showed dramatic footage of dead forests and empty lakes. Environmental groups organized rallies where protesters held signs reading "Stop Acid Rain Now" and wore gas masks to dramatize the invisible threat falling from the sky. The predictions grew increasingly apocalyptic as scientists gathered more data. Researchers warned that if current emission trends continued, entire regions of North America and Europe would become ecological wastelands within decades. Some studies suggested that acid rain could make large areas of the northeastern United States uninhabitable for most plant and animal life. Computer models projected the collapse of forest ecosystems across multiple continents. The scientific community spoke with unusual unanimity about the scale and urgency of the threat. What made acid rain particularly terrifying was its insidious nature. Unlike oil spills or toxic waste dumps which caused immediate and visible damage, acid rain worked slowly and quietly. A forest might look healthy one year and show signs of distress the next, with no obvious cause visible to the naked eye. The invisible killer fell from clouds that looked perfectly normal. Children played in rain that was slowly poisoning the environment around them. The media coverage reached fever pitch when scientists began connecting acid rain to human health problems. Studies suggested that the same atmospheric chemistry creating acid rain was producing fine particulates that could damage lungs and worsen respiratory conditions. Suddenly, acid rain wasn't just killing trees and fish, it was potentially killing people. The threat seemed to lurk everywhere, falling silently from the sky onto schools, playgrounds, and neighborhoods. Environmental scientists found themselves in the unfamiliar position of being taken seriously by governments and the general public. Congressional hearings featured dramatic testimony about dying ecosystems. European parliaments debated emergency measures to address transboundary pollution. Research funding flowed to laboratories studying atmospheric chemistry and ecosystem damage. For once, the scientific community's warnings about environmental destruction were met with genuine alarm rather than skeptical dismissal. The crisis mentality reached its peak in the mid-1980s when several high-profile studies confirmed the worst fears about acid rain's environmental impact. The National Acid Precipitation Assessment Program, a massive 10-year research effort involving multiple government agencies, documented extensive damage to forests, lakes, and streams across the eastern United States. Similar studies in Europe painted an equally grim picture of ecosystem collapse across the continent. Yet here's what makes the acid rain story so remarkable. The scientists were absolutely right. This wasn't environmental hysteria or media sensationalism blown out of proportion. The chemistry was sound, the damage was real, and the threat was genuine. Lakes really were dying, forests really were collapsing, ancient monuments really were dissolving faster than ever before in recorded history. The apocalyptic predictions weren't based on wild speculation. They were grounded in solid research and careful observation. The irony is almost too perfect. At a time when environmental scientists are often dismissed as alarmists or accused of exaggerating threats for political gain, acid rain represents a case where they got it exactly right. They identified a massive environmental problem, traced its causes with scientific precision, predicted its consequences with remarkable accuracy, and even proposed realistic solutions. And unlike so many environmental issues that drag on for decades with endless debate about causes and solutions, acid rain had a clear villain, measurable impacts, and obvious remedies. What happened next would prove that sometimes, just sometimes, human beings can actually solve the environmental problems they create. But first, the world had to accept that the scientists weren't crying wolf. The dead forests and lifeless lakes provided all the evidence anyone needed that this particular environmental apocalypse was very real indeed. When scientists actually got it right. The breakthrough that changed everything came on July 24, 1963, when Gene Likens and his research team were conducting routine water quality measurements at the Hubbard Brook Experimental Forest in New Hampshire. They expected to find rainwater with a pH around 5.6, which is what you get when water naturally reacts with carbon dioxide in the atmosphere. Instead, their instruments showed a reading of 3.7, nearly 100 times more acidic than expected and roughly the same acidity as orange juice. The team ran the test multiple times, convinced their equipment was malfunctioning. It wasn't. What made this discovery so powerful was that it happened at exactly the right place and time. The Hubbard Brook site had been established specifically to study long-term ecosystem health, complete with sophisticated monitoring equipment and detailed measurement protocols. This wasn't some random observation by a graduate student taking water samples for a class project. The research station had the infrastructure and credibility to document something extraordinary, and more importantly, to prove that it wasn't a fluke. Likens and his colleague Herbert Borman realized they had stumbled onto something much bigger than contaminated rainwater in one New Hampshire forest. They began expanding their measurements across the northeastern United States, collecting precipitation samples from dozens of sites. The results painted a disturbing picture. The acidic rain wasn't limited to areas near obvious pollution sources. Remote wilderness areas hundreds of miles from the nearest factory or power plant were receiving precipitation with pH levels that would make your dentist cringe. The eureka moment came when the researchers started mapping their data. The pattern became unmistakable. The most acidic precipitation was occurring downwind of major industrial centers in the Midwest. Sulfur dioxide and nitrogen oxides were being pumped out of smokestacks in Ohio and Pennsylvania, then carried by prevailing winds to fall as acid rain on forests and lakes in New York, Vermont, and New Hampshire. For the first time, scientists had connected specific industrial emissions to environmental damage occurring hundreds of miles away. In 1974, Likens and Borman published their findings in the journal Science with a paper titled Acid Rain, a Serious Environmental Problem. The timing couldn't have been better. The environmental movement was gaining momentum following the first Earth Day in 1970, and the public was primed to hear about new ecological threats. But more importantly, The scientific community was ready to take their colleagues seriously when they presented hard data about atmospheric chemistry and ecosystem damage. The research methodology was bulletproof in ways that environmental science rarely achieves. The Hubbard Brook team had established baseline measurements before the problem became severe, so they could document exactly how conditions had changed over time. They could trace the chemical pathway from industrial smokestacks to dying fish in Adirondack lakes. They had controlled experiments, long-term data sets, and reproducible results. When critics tried to poke holes in their conclusions, the scientists had answers backed by decades of meticulous measurements. The experimental work conducted at Ontario's Experimental Lakes area provided the smoking gun that sealed the case. Researcher David Skynler and his team did something that would make any environmental lawyer salivate. They conducted a controlled experiment that proved causation, not just correlation. By acidifying one lake, they proved fish died of starvation because acid dissolved their prey's shells. Within a few years, a thriving aquatic ecosystem had been reduced to a biological desert. The beauty of the acid rain research was its clarity. Unlike climate change, which involves complex feedback loops and century-long timescales, acid rain had a simple cause-and-effect relationship that anyone could understand. Burning fossil fuels releases sulfur dioxide. Sulfur dioxide reacts with water in the atmosphere to form sulfuric acid. Sulfuric acid falls as precipitation and kills stuff. The chemistry was straightforward, the impacts were measurable, and the timeline was immediate enough that researchers could document changes within a few years rather than decades. This simplicity made acid rain research almost immune to the usual tactics that industries use to muddy environmental science. The Edison Electric Institute, representing coal-fired power plants, tried their best to fund counterstudies and create doubt about the findings. But when lakes are literally dying and you can measure the exact pH of the rain falling into them, it's hard to convince anyone that the problem might be caused by solar flares or natural climate cycles. The cause and effect relationship was too obvious and too well documented to dispute convincingly. The scientific community rallied around the acid rain research with unusual unanimity. Atmospheric chemists confirmed the chemical pathways. Ecologists documented the biological impacts. Geologists showed how acid rain was accelerating the weathering of stone monuments and buildings. By the early 1980s, hundreds of peer-reviewed studies from multiple disciplines had confirmed the basic conclusions. Industrial emissions were creating acid rain, and acid rain was causing widespread environmental damage. What made the scientific response even more remarkable was how quickly researchers developed sophisticated tools to study the problem. The regional acid deposition model allowed scientists to predict where acid rain would fall based on emission sources and weather patterns, something no atmospheric model had accomplished before. Atmospheric monitoring networks tracked pollution as it moved across state and national boundaries. Ecosystem studies documented recovery rates for damaged forests and lakes. Within 2 decades, the scientific community had built a comprehensive understanding of every aspect of the acid rain problem. The breakthrough research created something almost unheard of in environmental science, a clear problem with an obvious solution. Scientists could point to specific smokestacks and say, install scrubbers on those and the problem goes away. They could model exactly how much emission reductions would be needed to restore ecosystem health. They could predict recovery timelines for damaged lakes and forests. Environmental problems are usually messy, complicated, and politically ambiguous. Acid rain was refreshingly straightforward. Perhaps most importantly, the scientists got their timing right. They identified the problem before it became irreversible, documented the damage while it was still occurring, and proposed solutions while there was still time to implement them. They didn't wait for perfect data or complete understanding before sounding the alarm. They saw a clear threat to major ecosystems and spoke up loudly enough to get everyone's attention. The result was a rare moment in environmental history when scientists made accurate predictions about ecological disaster and were actually taken seriously by the people who could do something about it. The research was solid, the threat was real, and the solutions were achievable. For once, environmental scientists found themselves in the unfamiliar position of being both right and heard. But here's where the story gets really interesting. The solution that saved entire ecosystems turned out to be surprisingly mundane. The most boring solution that actually worked. You want to know the really strange thing about solving acid rain? The technology that saved entire ecosystems wasn't some breakthrough invention or revolutionary green energy system. It wasn't solar panels or wind turbines or anything that would make for good photo ops at environmental rallies. The solution was so mundane, so industrial, and so thoroughly unsexy that most people never even noticed it was happening. We're talking about the environmental equivalent of fixing a global crisis with really good air filters. The hero of this story is something called a sulfur scrubber, which sounds about as exciting as it actually is. Picture a massive tower attached to a coal power plant filled with what amounts to a glorified car wash for smokestack exhaust. The process works like this. Scrubbers spray smokestack gases with limestone water, transforming sulfur dioxide into harmless gypsum. Instead of sulfur dioxide shooting out of the smokestack and eventually becoming acid rain, you get a wet paste that can be turned into wallboard for construction projects. The engineering behind scrubbers is so straightforward that it almost feels anticlimactic. Take polluted air, spray it with lime water, collect the sludge, and voila, no more acid rain precursors floating around the atmosphere. The technology existed in various forms since the 1930s, but it took decades for anyone to mandate its widespread use. The EPA's acid rain program created competition among different pollution control technologies, spurring improvements and innovations that drove down costs and increased effectiveness. Modern scrubbers remove over 95% of sulfur dioxide emissions, proving their remarkable effectiveness at industrial scale. The automobile industry contributed its own brand of boring but effective technology through catalytic converters. These devices look like metallic honeycomb structures stuffed into your car's exhaust system. Exhaust gases flow through chambers lined with platinum, palladium, and rhodium, which act as catalysts to break down nitrogen oxides and other pollutants into less harmful compounds. The chemistry happens at temperatures hot enough to melt copper, transforming molecules that would otherwise contribute to acid rain into nitrogen, oxygen, and water vapor. By 2000, every new U.S. car had one, cutting nitrogen oxide pollution by over 90%. What made catalytic converters particularly effective was their universality. Every new car sold in the United States after 1975 was required to have one, which meant that within a couple of decades, the entire fleet of American automobiles was equipped with pollution control technology. Unlike voluntary programs or incentive-based systems, this was a straightforward regulatory mandate that left no room for interpretation. Car manufacturers complained about the costs, but they had no choice but to comply. The fuel processing side of the equation involved equally unspectacular improvements to refinery operations. Coal washing became standard practice at many facilities, removing sulfur compounds before the coal ever reached a power plant. Petroleum refineries invested in hydrotreating units that stripped sulfur from gasoline and diesel fuel using hydrogen gas at high temperatures and pressures. The result was cleaner-burning fuel that produced fewer acid rain precursors when combusted. These technologies shared a common characteristic that made them politically feasible. They were invisible to consumers. People didn't have to change their driving habits, switch to different energy sources, or make any lifestyle adjustments whatsoever. The pollution controls worked behind the scenes, embedded in industrial processes that most citizens never thought about. Power companies installed scrubbers, automakers added catalytic converters, and refineries upgraded their equipment, all while ordinary people went about their daily lives completely unaware that an environmental revolution was happening in their exhaust pipes and electrical grid. The implementation happened with remarkable speed once the regulatory framework was in place. The Clean Air Act amendments of 1990 created a cap-and-trade system for sulfur dioxide emissions that gave power companies flexibility in how they reduced pollution while setting firm limits on total emissions. Some utilities chose to install scrubbers, others switched to lower sulfur coal, and many did both. The market-based approach allowed companies to find the most cost-effective solutions, while ensuring that overall emissions declined year after year. The success of these unglamorous solutions highlights something important about environmental problem-solving. The most effective interventions often happen at the source of pollution rather than trying to change human behavior downstream. Instead of asking millions of people to drive less or use less electricity, acid rain mitigation focused on making the cars and power plants cleaner. This approach avoided the usual political battles over lifestyle changes and economic sacrifice that derail so many environmental initiatives. The contrast with other environmental challenges is striking. Climate change advocates promote everything from electric vehicles to plant-based diets to carbon taxes, all of which require significant changes in how people live and work. Ozone depletion was addressed by banning specific chemicals and finding substitutes, which created some economic disruption but didn't require consumer behavior changes. Acid rain was solved with technology that made existing systems cleaner, without requiring anyone to use them differently. The boring nature of the solution probably contributed to how quickly the public forgot about acid rain as an issue. There were no dramatic announcements about revolutionary breakthroughs, no ribbon-cutting ceremonies for scrubber installations, and no consumer products marketed as acid rain solutions. The technology worked quietly and efficiently, removing pollutants from the air without fanfare or publicity. Success looked like the absence of news rather than the presence of dramatic improvements. Industrial solutions also had the advantage of being scalable and permanent once implemented. A single scrubber installation could eliminate more sulfur dioxide emissions than thousands of individual behavior changes, and it would continue operating for decades with routine maintenance. The technology didn't depend on sustained public interest or political support beyond the initial regulatory requirements. Once the equipment was installed and operating, it would keep working regardless of whether anyone remembered why it was there. The lesson from acid rain is almost disappointingly simple. When you have a pollution problem, the most straightforward solution is often to install better pollution controls. No protests required, no lifestyle changes needed, just better engineering applied at the right scale. It's the kind of boring success story that environmental movements should probably celebrate more often, even if it doesn't make for compelling social media content. But of course, having the right technology is only half the battle. Someone still had to make the political decision to actually use it. The policy miracle nobody remembers. The Clean Air Act amendments of 1990 represented something that almost never happens in environmental politics. When faced with a massive ecological crisis, governments actually worked together, moved quickly, and implemented solutions that worked better than anyone expected. If you're looking for evidence that international cooperation on environmental issues is possible, acid rain represents the closest thing to a miracle we're likely to see in our lifetimes. The legislative breakthrough wasn't just ambitious in scope or goals. What made this law remarkable was that politicians actually designed a system that worked. The amendments created the acid rain program, which established a permanent cap on sulfur dioxide emissions from power plants across the country. This wasn't some voluntary agreement or aspirational target that companies could ignore when it became inconvenient. It was a hard limit with real enforcement mechanisms and serious penalties for violations. The genius of the 1990 amendments lay in their use of market-based mechanisms rather than traditional command and control regulations. Instead of telling every power plant exactly what technology to install or which fuels to burn, the law created a cap-and-trade system that let companies figure out the most cost-effective ways to reduce their emissions. Utilities could buy and sell emission allowances, bank them for future use, or invest in pollution controls that reduced their need for allowances altogether. The system gave companies flexibility while guaranteeing that total emissions would decline year after year. This approach proved politically palatable because it recognized that different companies face different costs for reducing pollution. A utility with older, dirtier power plants might find it cheaper to buy allowances from a company that had already invested in clean technology. Meanwhile, the company with cleaner plants could sell its excess allowances and use the revenue to fund additional improvements. The result was a competitive market for pollution reduction that achieved environmental goals at a fraction of the cost that traditional regulations would have required. The political maneuvering required to pass these amendments involved legislative horse trading that would make seasoned diplomats proud. Environmental groups had to accept market-based solutions instead of their preferred approach of shutting down coal plants entirely. The coal industry had to accept mandatory emission reductions instead of their preferred approach of doing nothing and hoping the problem would go away. Electric utilities had to accept caps on their emissions, but gained flexibility in how to meet those limits. President George H.W. Bush deserves credit for making acid rain reduction a priority despite opposition from within his own party. Bush had campaigned on environmental issues and saw acid rain as an opportunity to demonstrate that Republicans could address environmental problems without destroying the economy. His administration worked closely with Congress to design a system that could attract bipartisan support, which in retrospect seems like something from an alternate universe, where politicians actually solve problems instead of just arguing about them. The international dimension of acid rain policy created diplomatic challenges that make current climate negotiations look simple by comparison. The problem was fundamentally transboundary, with pollution from power plants in the American Midwest killing fish in Canadian lakes and European emissions destroying Scandinavian forests. Countries had to overcome the basic prisoner's dilemma of environmental cooperation. Why should we reduce our emissions if our neighbors might not reduce theirs? The breakthrough in international cooperation came with the 1979 Convention on Long-Range Transboundary Air Pollution, which brought together 32 European countries plus the United States and Canada to address cross-border air pollution. This treaty established the framework for scientific cooperation and information sharing that would prove essential for developing effective policies. The convention grew over time to include more than 51 member countries, and expanded its scope to cover additional pollutants beyond the original focus on acid rain precursors. The US-Canada Air Quality Agreement of 1991 represented the kind of international environmental cooperation that diplomats dream about but rarely achieve. Both countries committed to specific emission reduction targets and established monitoring systems to track progress toward those goals. The agreement included enforcement mechanisms and regular review processes to ensure that both sides lived up to their commitments. Canadian officials had been pressing for action on acid rain for years, and the agreement gave them the tools they needed to hold American power companies accountable for pollution that was killing Canadian ecosystems. European cooperation on acid rain involved even more complex negotiations because the pollution crossed multiple national boundaries.